Okay, here's another example of composition of function. In this case, we have two rational functions. Every time I see rational function, what I like to do is that I like to factor them out. So for the function f, the numerator can stay the same, but the denominator can be factored out to a set of two binomials. The first term, x squared, can be rewritten as the product of x and x. So it goes there. What are two numbers that multiply together to give me back -6? But also added together to give me back +5. Well, that's going to be +6 and -1. So this is the factor for this denominator. For the function g, we'll recognize the facts that x squared minus 9 is a special case quadratic expression, which is the difference of two squares. So 9 can be rewritten as 3 raised to the second power, and x can be rewritten as x raised to the second power. I mean x squared, of course, but yeah. So this is the same as saying x minus 3 over x minus 3 times x plus 3. So that's how you factor out the special case of the difference of two squares. You keep the two terms inside of parentheses and put the minus sign in one parenthesis and put a plus in the other parentheses. Now for the domain of the function f, you take the denominator and you set it not equal to 0, and then you use the zero product property. Take each of these binomial factors, set it not equal to 0. So x plus 6 cannot be equal to 0. X minus 1 cannot be equal to 0. So for x individually, we get x cannot be equal to -6 and x cannot be equal to +1. For the g function, the domain can be found in the same manner, which is by taking the denominator and set it not equal to 0. And then using the zero product property, take each of these binomial factors, set it not equal to 0, and then you solve for x individually. So in this case, x cannot be equal to +3 and x cannot be equal to -3. And yeah, so that's how I find the domain of these two. Now note that in the function g, x minus 3 right here is a common term, and we get to cancel it out. And because we get to cancel it out, the point of this continuity, x not equal to +3, which comes from x minus 3 not equal to 0, is called the removable discontinuity, because we get to cancel out a common term that we take to find this point of discontinuity. But anyway, what about f of g of x? Well, f composite g in terms of x, which is f of g of x. Well, really, all you have to do is that you take the function g, which is right here. Use this one instead because the factor one is a little more difficult. And you replace all of the x of the outside function, which is the f function, with the entire function g. So that means we are going to have, let's see, x minus 3 divided by x squared minus 9. And then all over x minus 3 divided by x squared minus 9, my bad, and then raised to the second power plus 5 times x minus 3 over x squared minus 9, and then of course plus minus 6. Okay, now I want to make sure that all of these denominator in the denominator are the same. So this denominator here, this one right here, is actually x minus 3 squared all over x squared minus 9 squared. This one is actually 5 times x minus 3 divided by x squared minus 9 only. Right here. Yeah. So this is that, and this is that. Now the 6 here is actually minus 6 over 1. So I want to make sure that all of these denominators are the same. Well, I can do that by recognizing the fact that the least common the lowest common denominator, I should say, the lowest common denominator for all of these three denominators is x squared minus 9 raised to the second power. Well, I got x squared minus 9 raised to the invisible first power here. So if I just multiply this denominator by another x squared minus 9, which will prompt me to do the same thing for the numerator. And this denominator 1 by x squared minus 9 square, like that. Then I'm going to get the common denominator in the overall denominator that I'm looking for. So this is going to be equals to, let's see, the numerator stay the same, x minus 3 over x squared minus 9. And then all over, let's see, this is going to be x minus 3 square over x squared minus 9 square. And then plus, you can see it there, plus 5 times x minus 3 times x squared minus 9 all over, all over x squared minus 9 square, and then minus 6 times x squared minus 9 square all over x squared minus 9 square. And then group everything together because we have a common denominator. So this is going to be equals to same numerator, x minus 3 over x squared minus 9. And the denominator is going to be, let's say, I'll make it a little longer, like this. Let's see, x minus 3 square plus 5 x minus 3 times 5x squared minus 9, and then minus 6 x squared minus 9 square, then all over x squared minus 9 square. So what about this? What about the next step? Well, let's continue simplifying it a little more before we have to check for discontinuity at every step. So for this one, well, I have a fraction over another fraction. I can change this division into multiplication by keeping the numerator x minus 3 over x squared minus 9, and just flip the fraction in the denominator. So this go up here and this go down here, and change division into multiplication. So multiplying by the reciprocal of the denominator, I'm going to have x minus 3 squared plus 5 times x minus 3 times x squared minus 9, and then minus 6 times x squared minus 9 square. So yeah, this is x squared minus 9 square, and keep, and then bring x squared minus 9 square. Well, I know that I can cancel out this and that. So this can be rewritten as x over 3, x minus 3 times x squared minus 9 all over x minus 3 square plus 5 times x minus 3 times x squared minus 9 minus 6 times x squared minus 9, and then square, like that. I'm going to take this whole denominator and I'm set it not equal to 0. Well, that's going to be a little difficult because I have a whole chunk here. But the idea is that, how do we know that whether or not there's any restriction at this step? Well, let's see. What I like to do is I like to observe this whole denominator and try to see if there's any x value that would make this entire denominator equal to 0. What I'm trying to say is that instead of taking this whole long denominator and set it not equal to 0 in order to find the x value that would make this denominator equal to 0. I'm just going to take a look at each binomial factor, x minus 3 and x squared minus 9. If I take this right here, if I take a look at this binomial factor x minus 3, and I ask myself, if I take x minus 3 and I set it not equal to 0, then x cannot be equal to positive 3. Well, let's just say if x equals to positive 3, and I plug it in here, I get 3 minus 3, that's 0, 0 squared, hey, that's going to be 0. And then I plug 3 in here, well, 3 minus 3 is 0. Anything multiplied 0 is 0, so I get 0 plus 0 right here. If I take x equals 3 and I plug it in here, I get 3 squared, which is 9. 9 minus 9 is 0, but hey, anything multiplied 0 is 0. So I get 0 plus 0 plus 0 when x equals to positive 3. So that's why I know that I had to exclude it out. What about this one? Well, let's see. For x squared minus 9, not equal to 0. That means x cannot be equal to plus or minus 3. So that means x cannot be equal to positive 3, and x cannot be equal to negative 3. Well, that is true because, you know, we mentioned it earlier. If x equals to positive 3, then hey, the whole denominator is going to be 3, so that's going to be undefined. What about negative 3? If x equals to negative 3, then I get negative 3 minus 3, which is negative 6. Negative 6 squared is going to be positive 36. When I plug x equals negative 3 in here, I got negative 3 minus 3, which is negative 6. 5 times negative 6 is negative 30. And then 3 goes in here. Well, negative 3 raised to the second power is going to be positive 9. 9 minus 9 is 0. Anything multiplied 0 is going to be 0. Negative 3 plug in here. Negative 3 squared is positive 9. 9 minus 9 is 0. Anything multiplied is going to be 0. So this becomes 0, and this becomes 0 when x is negative 3. But this will not become 0. This will be positive 36. So this whole denominator is not going to be 0 at all. So we don't have to worry about this. We just have to worry about this. Okay? So x cannot be equal to 3 at this step. What about all of the previous steps? Well, let's go back to this one. Of course, if we take a look at this denominator, we know that x cannot be equals to negative 3 and 3, just like what we did on top, right? And of course, same thing for this denominator. X cannot be equal to negative 3 and 3. So this is all of the restriction at this step. What about this step? Well, same thing. X cannot be equal to negative 3 and 3. Something right here. X cannot be equal to negative 3 and 3. X cannot be equals to negative 3 and 3. And x cannot be equal to negative 3 and 3. Okay? So this is all of the restriction at this step. What about the first step? Well, let's see. Well, first step is going to be the same thing. You know, this right here, this denominator, x cannot be equal to negative 3, comma 3. And same thing for this denominator. Okay? All of this, actually. Yeah. So, yeah, at every step, these are all of the restrictions. X cannot be equal to negative 3, right here, and right here. So that means the domain of f of g of x is going to include all of the restrictions of the result, which is x cannot be equal to positive 3, and all of the restrictions of every step of the way. X cannot be equal to negative 3 and positive 3, as well as all of the restrictions of the inside function, which is also x cannot be equal to positive 3 and negative 3. So really, it's the domain of the composition of function after we consider all of the restrictions of the inner function, g of x, x cannot be equal to 3 and x cannot be equal to negative 3. And all of the restrictions of every step of simplifying this composition of function, which is x cannot be equal to negative 3 and positive 3, right there. Okay. So main is going to be all real numbers except x cannot be equal to negative 3 and 3. So if you were to draw it on the number line, it's going to look something like, so there's a number line here, this is negative 3 and this is 3. So we are excluding negative 3 and 3, so from left to right, we have to go from negative infinity up to negative 3. And I put the parentheses because we are excluding it. And then for the next part, we're going to include the union side, which is or, which stands for or, going from excluding negative 3 all the way to excluding positive 3. So it's this part. And then for this one, union, from excluding 3 all the way to positive infinity. So that's the interval notation of f of g of x. And g of f of x is going to be found in the same manner. Just make sure that you take the entire f function, and then you replace all of the x of the g function with the f function.